speakers, may I invite you into the round table? Please fill the empty round table first. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. To the Honorable, the Rector of Universitas Trisakti, Professor Dr. Insinyur Kadarsa Suryadi DEA, to the Honorable Director General of Research and Development, the Ministry of Higher Education, Science and Technology, Republic of Indonesia, Dr. Fauzan Aziman, ST, Master of Engineering, the Honorable, the Dean of Faculty, Industrial Technology, Universitas Trisakti, Professor Dr. Insinyur Rianti Dewi Sulamet Aryo Bimo, ST, Master of Engineering, IPU. The Honorable Vice Dean 1 of Faculty Industrial Technology, Universitas Trisakti, Dr. Insinyur Nora Asmi, MT. The Honorable Keynote Speakers, Mr. Taryono Purba from Toyota Motor Manufacturing Indonesia, and Mr. Naga Rajan Ragawan. The Honorable Guest, Professor Yuji Sato from the University of Osaka, Japan, Professor Arif Budiman from Oregon Institute of Technology, USA, Mr. Wijanarko MSc, Director of Technical and Government Affairs, Toyota Motor Manufacturing Indonesia, Mr. Irwin Tristanto, General Manager of Engineering Division, Toyota Motor Manufacturing Indonesia, and Professor Manabu Enoki. Thank you for coming again. The Honorable, the Chairman of ISTA-AM 2025, Dr. Zaki Saptari Saldi from Universitas Pembangunan Jaya, and the Honorable Deans, Directors, Vice Deans, Head of Bureau, Head of Unit, Head of Department from Universitas Trisakti and fellow universities, and to all participants that could not be mentioned one by one. Hi, my name is Prayang Sani Julia, and we would like to say welcome back to the second International Conference on Science, Technology, and Applications of Additive Manufacturing ISTA-AM 2025. Thank you so much, ladies and gentlemen. And as we know previously, ISTA-AM 2025 already held the opening ceremony yesterday, and today is the second day of ISTA-AM 2025. So, ladies and gentlemen, as the opening address for today, let us hear the remarks from the Director General of Research and Development, the Ministry of Higher Education, Science and Technology, Republic of Indonesia, Bapak Dr. Fauzan Aziman, ST Master of Engineering. And in this opportunity, Bapak Dr. Fauzan will deliver through online platform. Therefore, please welcome to Bapak Dr. Fauzan Aziman. Time is yours.
Thank you very much. First of all, just checking, can you hear my voice?
Yeah, sure, loud and clear, sir.
Okay, thank you very much. Good morning, very good morning, everyone, to honorable guests and also hosts, especially to Director of University of Trisakti, Professor Kadarza, and also all the leaders of the university, and then all speakers, and particularly our appreciations to Professor Zaki Saldi as the chairman of the conference, and our very close colleague, Professor Arif Budiman, who is always very enthusiastic on the field. Allow me to open today's conference with a few key points that we at the Ministry of Higher Education, Science and Technology feels that additive manufacturing as one of the key frontier technologies in the world, the wave is coming to Indonesia. And again, I would again say that my apologies that I'm not able to join directly in person at Trisakti University due to my other activities at the moment overseas. So let me share my screen to give a context to my opening remarks. So I'll explain a few key points that how we would like to support frontier technologies such as additive manufacturing in the context of applications, and then how their R&D impact could be very useful for our future trajectory of economic development. And just a very short introductions of my background. So as Director General of R&D, I work as well as an expert staff at Danantara. So this is probably a strong intentions of the government that we would like to link between R&D and economy through investment and commercializations of research outputs seriously. I've been working as well as a young professor at Institut Teknologi Bandung for the last 8 years. And also I could probably proudly say that I was appointed firstly by Professor Kadasa, the director of Trisakti now, when he was rector of ITB. And it might probably be useful as well to explain that I co-founded a company in the UK called Alloyd, and Alloyd specifically is a company focusing on new discovery of materials, specifically metals, and also working deeply in the area of additive manufacturing. So this is a topic of my enthusiasm and interest as well. So it is a shame that I'm not able to join, but hopefully next time when the schedule is not clashing, surely would like as well to have some coffee chat with everyone's joining. Let me start with just a key background why we think 3D printing is important. So 3D printing is identified as a technology that changed very rapidly and in fact could be exponentially. But I think at the same time, due to the rapid change of the technology, ideas, and also development of technologies itself, somehow we may be able to be part of the journey. So that is key why 3D printing or additive manufacturing, something could probably transform the way we do R&D. So this is as well, despite on application side, we understand that Indonesia it's not well used, especially for the metals, but the technology transfer and then skills that we could build through additive manufacturing could be impactful for the society. And the way we see frontier technologies in Indonesia, especially in the development of ecosystem, so at MOHES of our Ministry of Higher Education, Science and Technology, we built 4 key strategies. This is, again, we do have opportunity and also challenges at the same time. A key opportunity for Indonesia is by 2045, 65% of our population will be in the productive age group. So which means that we will have sufficient inertia to move our ship towards advanced countries. But we do have a key challenge, especially on total factor productivity, which may stall the way we develop things if we don't really strategically put intention and also our policy correctly. So for that reason, what we are describing here is how we build Indonesia's knowledge-based economy. And one of which we feel for so long Indonesia in the past based on agricultural economy, and then now we are shifting too fast where we are focusing on services. So there is a big gap in between, which is manufacturing. And manufacturing itself has been moving fast as well. So in the past, big companies developing big manufacturing facilities, but about 10 years ago in Europe, flexible manufacturing becomes more and more important. Even in Japan, it started in the 90s and early 2000s. And then the additive manufacturing that started to kick off as well, where economic of scale of additive manufacturing becoming more and more relevant. Now, how do we see additive manufacturing itself? So additive manufacturing could assist a number of key under development. So it is somehow we would like to treat it as a matter of technology, because manufacturing itself will bring a number of contributions, not only to the manufacturing, but also to, say, renewable energy, agriculture technology, healthcare, so on and so forth. So this is where we see why we need to invest in terms of how material and manufacturing all together as an ecosystem could be a bridge to the key movement in Indonesia, where we want to shift from extractive economy towards more product-based economy. So on the left-hand side, we do have some in a pretty abundant state of material resources. And then at the same time, on the right-hand side, Indonesia is, with our populations, we do have pretty large markets as a consumer of EV, motor inventor, and then also, of course, electric charging stations, so on and so forth. So this ecosystem is growing very fast in Indonesia. And then material and manufacturing become very key that we would like to develop within the countries. Of course, we cannot develop alone, so we need to collaborate, but at least we need to be strategic on development within the country to optimize added values of our investment, of our research and development, and also talent development. Now, these are just some examples. I'll just go through a few examples where applications of additive manufacturing, which it seems to be the key underlining subject of the conference. So on the right-hand side, if we break down a few key, say here just EV ecosystem, it's not only EV in terms of cars and then motor, inverter, battery, but also we are talking of the energy flow through this. So PV, CSP, wind turbine, some of these are now 3D printed. And we see the benefit of the value supply chain could be added to this ecosystem is pretty massive. And then it's all about how we can really position ourselves on how to use the technologies with the right demand and also supply chain. So I think applications and supply chains could not be separated. And then supply chains that we are talking, at least here, both material flow supply chain and energy flow supply chain could be affected by development of additive manufacturing. Now, let me go through just quickly with my past experience on this. So this is printed in the company that I co-founded. So we printed a number of AM for different applications. So on the right-hand side, I think TPMS, something that you know all very well. This is gyroid base. We built this, for example, for a heat exchanger for Ferrari GT F250 at that time. And then also we built something similar for a heat exchanger in the fuel tank for Boeing. So as you can see that there's then lateral thinking way where applications in aerospace can be then used in, say, in Ferrari GT. And that is the beauty of additive manufacturing. So once you tackle the technology in one area, you can move to other areas pretty much without too much investment. So I can then go through a few of applications as soon as we handle the way how we can print well. So on the left-hand side is the technology that we built. So the company based in the UK. And on the left-hand side is engine chamber, combustion chamber for satellite that we built. We patented the materials. It is a nickel-based materials. And then we designed, we printed, and on the right-hand side is testing. And it is now approved by ESA to be launched in 2026 in mission. And then we also then implement in biomedical. So this is something which I think in Indonesia could be very scalable. The only thing with biomedical is on the standardizations and certifications. So in the past, it took us 3 years to get ISO, relevant ISO, so that we can produce and then can be then used by people. And I remember I did ask one of our teams how many documents we produced to get the ISO certification. And then my team counted. So we produced around 7,000 documents just to produce ISO certificate for biomedical 3D printing. So along this line, just to mention that it is not all about technology, but also it's all about industrial standardizations that we need to be part of. So something which hopefully we can discuss more and more in Indonesia and to support. And before joining the ministry, I used to work as an academic at Oxford University, particularly at Rolls-Royce UTC at Oxford. And I can also tell that Rolls-Royce is developing AM pretty intensively. And then I then also work to develop GE9X engine for Boeing's 777X. And then they do also something similar. So the idea again, because with AM, you cannot just easily use existing materials. You need to modify materials in a way so that your 3D printed parts will be competitive. So research in this area is actually multidimensional in a way. So that is also exciting at the same time, also challenging. So with that reason, so let me bring back to the policy of our ministry. So we shifted the way we do research at the moment. So in the past, our research based on topics, based on products that we would like to develop. So we transformed this that our research will be focusing on problems or challenges. Also, we call it challenge-based ecosystem. By doing so, hopefully we then build a multidisciplinary ecosystem within the country. And then we are putting forward as well sustainability in our economic growth through research-driven or deep tech economic transformations. So hopefully that explained on the background of our policy and the way we see additive manufacturing, and then in the context of also my past experience. So let me just quickly, probably just a few minutes, just to explain quickly, and then the relevance of this could be useful for discussions, as we are now launching two programs. So we have only two programs for next year, 2026, in the ministry in terms of R&D. First is what we call it priority research program, and second is strategic research funding program. By priority, it means that we try to improve equity or distributions of research across Indonesia. So this, we have around 3,000 universities under the ministry. In total, in Indonesia, there are around 4,500 universities. So we need to work very well with the distributions. And priority research program will focus also to involve as many as possible our young fellows so that they can really start doing research at high quality. And then the second is what we call a strategic research program. So in strategic research program, we fund much more than on the left-hand side. So in fact, the strategic research program could be 10, 15 times higher than priority research program in terms of funding size. And the idea here is that we would like to be strategic in solving some of the key problems in Indonesia, and one of which is advanced manufacturing. So we welcome collaborations in the future, and also funding scheme that we can support. These are a few funding schemes. So from talent development, research, which include as well international collaborations, partnership with industry, and also other governmental bodies. We also have key areas around downstream industry research that include hackathon and also sandboxing, which is testing. So which means that this may be relevant for 3D printing, because once you 3D printed, you need to do a lot of testing. And our program can fund up to 2 billion rupiah, or in Bahasa Indonesia, 2 miliar rupiah per product tested for 2 years. And now I jump a little bit. So how do we then see all those funding schemes? So we are providing funding schemes from the leftmost and side of R&D, so upstream, so where governments need to really support. But then we are pushing forward as well higher TRL, supporting in a way that market scaling can be done. So with that in mind, we then create this research roadmap for 8 strategic national industries, and then I can safely say as well relevant to today's conference, because manufacture and advanced materials identified as one of the 8. And we also provide information. So if you would like to see research done in Indonesia, you can contact us. So this is something that can be accessed publicly. These all are research that we do for the last 5 years, and we have around 67,000 research across Indonesia. And as you can see that if you click, you will see where the location of research was the team. And then I also try to search AM, additive manufacturing, 3D printing. And in fact, we have around 95 research at the moment. So if you compare 67,000 research that we do, we only have 95 research with keywords AM, additive manufacturing, or 3D printing. So this doesn't separate yet metals and non-metals. But then if I click one of this within this 20, so you'll see that someone is already doing AM for A6061 aluminum using essentially welding for arc additive manufacturing. So what I would like to say as well, that despite AM might be expensive yet in Indonesia, but development of AM, so in the past my background was also computational scientists or engineers for welding simulations. And then welding simulations, in fact, one of the most difficult simulations in my experience, because it involves a lot of phases, a lot of transformations of materials, and so on and so forth. And that links to a point that when we develop applications of AM, it doesn't mean that we just need to focus on the AM itself, but also we can focus on the few key topics relevant to AM, which can be even nowadays can be done in Indonesia, and one of which, of course, welding, for example, because in principle it is very close. Despite its scale size, it's different, but there are some similarities. So hopefully that give a good pointing discussions that can be continued today, second day of the conference. And I would like to close that let's build collaborations more and more. My appreciation as well that today's conference attended by overseas scientists and professors. So I would like to appreciate that because we feel that innovation isn't just about science and technology, but collaborations. Thank you very much, and hopefully you will enjoy a lot of discussions and fruitful outputs from the conference today.
Please give applause, ladies and gentlemen. Thank you very much to Dr. Fauzan Aziman as the Director General of Research and Development, the Ministry of Higher Education, Science and Technology, Republic of Indonesia. Ladies and gentlemen, and after this, we would like to invite as well our Honorable Board of ISTA-AM. Please welcome to Professor Arif Budiman from Oregon Institute of Technology, USA.
Oh yeah, okay. Good morning, everybody. And good morning as well to Dean Rianti, as well as all our international speaker. First of all, my name is Arif Budiman from Oregon Tech. And on behalf of the Scientific Board of ISTA-AM 2025, I am also the past chair of ISTA-AM 2024. We would like to extend our utmost gratitude for Pak Fauzan. Thanks, Pak Fauzan. It's very inspiring opening remarks. It's not only an opening remark, it's really putting in context of what we've been doing really in this conference since last year, this year. I'm really excited. You show the 3D design of lattice structure for aerospace, as well as space rocket, and also biomedical. That's dear to my heart, make me excited inside. And your work in your company, it's also really inspiring, Pak Fauzan. Thanks a lot for your support, your strong support, as well as from the Kemendikti Saintek, as well as from Pak Satrio, our advisor. I mean, both Pak Fauzan and I share, having Pak Satrio Sumantri Brojonegoro as our final year advisor in Bandung Institute of Technology. I would like to use this opportunity, maybe just 1 or 2 minutes, to thank everybody, especially in Trisakti, Dean Rianti for strong support, as well as a lot of other people in Trisakti. I think it's been great conference. I enjoy many of the talks in both conferences, ISTA-AM as well as ICADME, and it's not possible without the support, the strong support from Dean Rianti and everybody in Trisakti. I would like to also say thanks to many people who are online right now in the Zoom. I think, well, a few are actually my very close colleague. I think there is Professor Nagarajan Ragavan. We were in Singapore University of Technology and Design together for many years, so he will be giving a keynote seminar soon. There is also, I think, Dr. Mark John, I saw in the participant list, Professor Jupiter Manurung, our close colleague again. We are discussing a lot on the potential collaboration in additive manufacturing, as well as, of course, Prof. Manabu Enoki from Tokyo University of Technology, Prof. Sato from Osaka University, as well as our keynote speaker from Toyota. It's great to have our industrial partner to give an industrial talk in our conference, and also for strong support from Toyota. We really extend our utmost gratitude. Last but not least, please allow me to thank our chairman, Dr. Zaki Zaldi, as well as our de facto vice chairman of this conference, Pak Pandang Juana. This conference is mostly Pak Zaki and Pandang. I mean, of course, I help with a lot of things with the network, but all the things that you have, the souvenirs, the booklet, it's basically the great work of Pak Zaki and Pandang. So again, on behalf of the scientific board, so I think Professor Tim Pasang from Western Michigan University, a very close friend of mine, 35 years. We were in the same department together in Monash University back in 1995. I'm old. So Prof. Tim Pasang is we started this conference really on a trip in Crater Lake near Klamath Falls when Pak Zaki visited us in OIT. That was back in 2022, right, Pak Zaki? Or 2023. And it's just over coffee, and we think that, hey, we are so excited about talking about additive manufacturing, but at the same time, the three of us are all Indonesian. We say that, well, we know quite a bit about additive manufacturing. We want to contribute what we know about additive manufacturing, about what would be important for Indonesia soon enough, in the future, but soon enough. So that was the beginning of it. And so on behalf of Prof. Tim Pasang, Prof. Wang from Taipei Tech University, Prof. Sukamoto from Osaka University, myself, and also Pak Satrio Sumantri Brojonegoro, of course. They have Pak Satrio has been supporting us since day one of this conference, as well as Pak Fauzan. So on behalf of the scientific board of ISTA-AM, thank you so much, Pak Zaki. You did a great job. You did a wonderful job, super job indeed. And yeah, I mean, all these things it will not happen, will not be possible if not for you, and also Pandang. So with that, I think that's a few minutes from me. Thank you so much. I hope that, I mean, I will actually leave for airport in about half an hour. So I hope we can meet again 2026 ISTA-AM. Hopefully we will meet again, and I will be looking forward to meeting all of you still next year. Thank you very much. Good morning.
Yes, thank you very much to Professor Arif Budiman as the Scientific Board of ISTA-AM 2025. And safe flight, Prof. Arif, and hopefully can meet you again in another opportunity. All right, so ladies and gentlemen, after this we will heading into the keynote speech session, and the session will be led by our moderator, Bapak Dr. Zaki Saptarisaldi from Universitas Pembangunan Jaya, as well as the chairman of ISTA-AM 2025. So please give applause, ladies and gentlemen. So please join. Thank you very much, Bapak Dr. Zaki. Firstly, let me introduce briefly for Dr. Zaki. Dr. Zaki Saptarisaldi, he obtained his doctoral degree from Delft University of Technology, the Netherlands, and currently he is an assistant professor at Department of Product Design, Faculty of Technology and Design, Universitas Pembangunan Jaya, Indonesia. His teaching and research interest lies in the area of thermofluids, material processing, metal additive manufacturing, and product development, with a primary focus on the use of computer-aided design and engineering, including computational fluid dynamics or CFD simulations. Dr. Saldi's research experience includes fellowship in a project funded by European Union on computational modeling of syngas combustion, and in a project funded by the Engineering and Physical Science Research Council, United Kingdom, on integrated safety strategies for hydrogen storage on board fuel cells vehicle, both carried out at University of Warwick, the United Kingdom. So that's the brief introduction of Dr. Zaki, and in this session we'll pass to Dr. Zaki. Please, Dr. Zaki, time is yours.
Thank you very much, Mbak Praya. Good morning, everyone. Thank you for joining us again in this session. Thank you, Pak Arif. So for the first keynote speakers, I would like to introduce our industrial keynote speaker. Thank you for joining us, Bapak Taryono Purba. Bapak Taryono Purba is the Deputy General Manager from PT Toyota Motor Manufacturing Indonesia, Timin. He is a manufacturing professional with over 20 years of experience in maintenance, production, and engineering. With a master's degree in industrial engineering and a background in electrical engineering, he has led various strategic functions at Timin, such as Division Head of Engine Production in Karawang, Department Head of Vehicle Assembly Production, and Department Head of Sunter Engine and Casting Plant Maintenance. Without further ado, I would like to invite Bapak Taryono Purba to deliver his industrial keynote speech. Welcome, Pak. Silakan, Pak.
Okay, good morning, everyone. The Honorable Prof. Zaki and also Prof. Enoki-san from Tokyo University Technology, and also Sato-san from Osaka, and Pak Andang, the Honorable, and also very sorry that I cannot mention one by one, but I'm so nervous to be here because usually we talk in casual, but today we would like to talk in looks like academics style, so very sorry if I am becoming so nervous. Maybe we can start the slide, yeah, please. Okay, I would like to share about the one of the applications of additive manufacturing in industry. And this is about the laser cladding, maybe like looks like a laser welding, yeah. And this will be the first technology that we applied in our engine plant. Okay, next. Delay. Okay, this is just about my background. Actually, I'm coming from electrical engineering. So I graduated in 2004. Oh, 70, so this has been a long time. And I just take my master degree after 20 first years. Yeah. So this is very long time, yeah. Because actually, when I take my master degree, I want to motivate my son and my daughter. So I took my master degree, but in supply chain management. But after I got master degree, I think I'm getting addicted in study, and maybe I would like to apply doctor, if there is an time and money, of course. Okay, I'm experienced in engine production division, and now also in charge in engine production Karawang division. Okay, next. Maybe this is just an introduction of Toyota Motor Manufacturing. Yes, we are producing not only vehicle but also component and also engine. And 70% component now is localized, and we are OEM of the 7 vehicle and 4 engine types, and we have together with Toyota Astra Motor have around 38 dealers, and also external partners for the export our product. Maybe our direct employee is currently around 8,000 employees, but if surrounding all of the supply chains, this is maybe around more than 300,000 employees. And now we develop like XEV center, yeah, to like introduce our electrification era. Next. This is our plan. Actually, we have 5 plans. 2 is our vehicle plan, and the others 3 is we consist of the engine plan, and the one separated is casting plan. So if we see the like Innova, Fortuner, it's made in the Karawang plan number 1, and for the like medium size car like Veloz, Yaris Cross is made in Karawang number 2. For the other plants, Sunter plant is producing our engine for TR engine that's utilized for the Innova gasoline and also Fortuner gasolines. And for my worksite in Karawang plant 3, actually this is producing NR engine that utilized for the Yaris Cross and also Veloz. And just last week, we introduced our new model, Veloz Hybrid. This is a hybrid for all. So if you interest for the hybrid, please buy hybrid. This is just an advertisement. Okay, and for the engine itself, we have 2 kind of engine, yeah, TR series and NR series. And actually, we plan to introduce the new type of engines in the next 2 years, and starting from now, we just in production preparation. This is M series engine, and that engine will utilize the laser clad technology. And just for the
Aplikasi di ini ya, Luka? Di email.
okay, for example, our product is not only for domestic, yeah. We also delivering to the export. If we see the trend, yeah, we just got the 1 million export from 1971. It took around 47 years, yeah, to get 1 million export. But to get the 2 million export, we just need 4 years. And just this year, we celebrate the 3 million export just 3 years after 2 million export. So our producing is increased so well. Yeah. Next. Next, please. And this is we try to the architecture of the vehicle itself. This is a Toyota New Global Architecture. Maybe we can show also this is in the YouTube channel because this is available there. And our feature, for example, like the lower hood that improve the driver visibility and how we improve the center of gravity of our body and how we optimization the wheel motions, wrist suspension is increased, higher body rigidity, and today we would like to focus in the dynamic force engine that this is have related with the additive manufacturing. Please, next slide. Maybe this is the simple video of the dynamic force engines. Maybe we can run the video, please. Okay. For the video. This is PDF or PowerPoint? Okay. Please say about the dynamic force engine. Actually, by this dynamic force engine, we can increase our efficiency and also the power itself. So by the more small capacity engine, we can improve our power. So mean less efficiency. How to make this? Of course, we need more efficient combustions. Make a tumble combustions. And to make this, need the more wider intake manifold. And this is possible to make this wider intake manifold by additive manufacture. Because if we use the conventional process, usually the conventional engine use the press fit for the valve seat. This is cannot making the like direct supply of the fuel, so cannot make the more efficient combustions. Okay, that's the dynamic force engine that require the laser clad in its valve seats manufacturing. Next. Okay, so this is one of our manufacturing to make the cylinder head. This is actually the one component of the engine itself. Usually we utilize the press fitting of the valve seat, as I mentioned. But to make the dynamic force, this is required the laser clad or welding, welding in this valve seat. So we introduce the new process of the laser clad valve seat intakes. And this is maybe will be the first time we introducing this process, so we need more deep study. Okay, next. Why this is required laser clad? Because if press fittings, this is there is a sectional area, so the fuel cannot directly coming into the combustion chamber. But if we use the laser clad, this is possible to make direct, like non-sectional, the fuel coming into the combustion chamber. So this is make like increased flow coefficients and also downsizing the design itself. So by making the smaller engines and more reduce the cross-sectional patterns, this is can improve the efficiency of engine itself. So this is making it possible to make like we call the tumble combustions rather than swirl combustions. That's the benefit of the laser clad itself. Next. And this is maybe the major components of the laser claddings. There is 4 components: the laser oscillator, and then powder feeders to distribute the powder itself. Next. And the important component is actually about the nozzle of the powders, and also the powder itself. We have to find the best composition actually for the powder, because in some journal mentioned that it should be in between that's cuprum or the alloy that should be mixed, in which composition is will be best compositions. Next. But also in the laser clad, we have facing many challenges. Actually, this is based on the previous experience in our regional country that already produced this engine. For example, non-bondings. Looks like there is not unity in the casting layer and the additive material, and also possibility for the crack. That's two challenges usually facing in this process. So what we prepare to overcome this challenge, actually we already making some activity. Next. For example, for the non-bondings, we already taken some possibility of the generating factor, and that's why by knowing the generating factor, we can anticipate or predict what we want to do. Actually, if we see the surface, sometimes non-bonding is distinguished by the other factor. Actually, this is like porosity or the inclusions, but the non-bonding usually looks like line defects in our product. Next. And this is for the crack. We already gathering informations from our affiliates on some finding issue in some journal. Actually, we find some possibility of the cracking, and by knowing this some possibility, we hope that we can gathering the preventive activity to protect the defect coming to our lens. Okay, next. And actually, this is the laser clad success factor that we already gathered, and some our preventive activity to protect the non-bonding and also the crackings. And of course, not only in process optimization, we also conducting the product checks, like the traceability and data gatherings to predict our process trend. Maybe in more detail, we can see the next slide. For example, to protect non-bending, we have to secure that our powder material, so we select the coaxial method. Actually, in the laser clad, there is two methods. Yeah. First is about the outer layers of the powders, but we select the coaxial, means the powder also gathering coming into the nozzles. That we would like to take during our process. Okay, next. And this is some machine parameter. We also gathering from some journal and also some the preliminary of the other plans, such can the powers of the laser oscillator, and then the powders compositions. We try to define like the increasing laser power, higher scanning speed, and also the powders feeding rate. That's some parameters we try to gatherings to make our good product. Okay, next. Maybe this is the ends our presentations. Actually, we invite the collaborations, as also mentioned by Mr. Fauzan, that the innovation is not just the science and technology, but this is collaboration. I think this is enough, yeah, with our slide, yeah. So we invite like the triple helix approach. Usually we just gathering the information from our mother plants, our regional factory, to getting some non-defective conditions, but we try not to also including the STEM, yeah, like scientists, technology, engineering, and manufacturing to provide a good product in ourselves. So we are ready to producing the laser clad in the nearings this years. I think that's enough of my presentation, and we open for the further collaboration. Thank you very much.
Thank you very much, Pak Taryono. I would like to invite you to take a seat here. So now before we move to the second presentation, I would like to open the session for questions from the audience. Please introduce yourself, Pak.
I am Tono Soekarnoto from Mechanical Engineering. I would ask to Pak Taryono, is the laser clad process used to join the valve seat to the first question, yeah? Is the laser clad process is to join the valve seat to cylinder head? And the second question is, can you explain more detail the benefit of the laser clad? But because when you present, you just tell that increasing thermal efficiency, I forget how many percent. I mean, the benefit of the laser clad is worth or not compare with the engine performance increase. That's my question. Thank you.
Thank you, Pak Tono. Oh, thank you, Pak Tono. Maybe directly to answer, Pak Sagi. Okay. Maybe before I answer my questions, please welcome Prof. Rianti. Yeah. You just see. Prof. Rianti visit our plant last year, yeah, Prof. Yeah. Thank you for your visitations. Okay, now I would like to answer Pak Tono questions. Yeah. Is the laser clad to joining the valve seat to cylinder head? No. Laser clad is to forming the valve seat. It is to replace the valve seat. Maybe we can go to the, my slide. In my slide presentation, yeah, in the differences between the press fitting and also laser clad. Can we go to my presentation? Because the current engine utilize press fitting, mean the valve seat is coming the other part. This is like sintering material, and then this is press fit. But if we press fit, if you back to the, maybe this is the first slide, yeah. No. Okay. More. Next. Next, maybe this next slide. Next. Okay. This one. This is the valve seat, yeah. Actually, this is generated by the press fitting. But for the dynamics force, this is need to make a tumble combustions. Yeah. If we utilize the press fit, the degree of the valve positioning is cannot open. This is too narrow. That's why it can make a swirl combustions. That's why we to open more the gasoline coming from this port, yeah, to directly to the chamber. The process that's making it possible is laser clad, because this is a need a thin layer. If we utilize the press fit, this is cannot make a thin, and because this is very narrow picture. Actually, if this is more figure, we can see that the fuel is cannot coming directly. Maybe we can see there is a degree here. There is a degree. So by forming the valves, forming the seat utilize the laser clad, this is possible the fuel coming to the combustion chamber. That's the laser clad benefit. And about the seconds, benefit of laser clad. Actually, the benefit of laser clad, that's making the possibility to make the tumble combustion. So because this is have reducing the sectional area and also make downsizing. This is need the just a thin layers of the seat itself. If we make by the press fit, this is maybe so tough, yeah. No, cannot be a thin layer. That's maybe Pak Tono. Hopefully you can. That's maybe the difference of the academic and practical. Yeah, maybe sorry, I cannot. But we have proven, yeah, in our performance. This is mentioned 40% of our performance engines. Okay. Yes, welcome.
Thank you, Pak Tono. I hope that answers your question, Pak.
Thank you. Pak Tono.
Okay. Maybe I take one more question from the audience.
Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the opportunity. Thank you for your presentation, Pak. It gives us many insight regarding the automotive technology. I think my comment is improvement valve seats from press fit to laser cut. Very interesting. It improve just like Bapak said. It improve the fluid flow in the internal combustion engine, so the thermal efficiency of the engine will increase. In my question is, how about the durability of the laser cut itself, compared to the common technology like valve seat with using noble alloy, just like nickel-based alloy? Maybe the common issue in valve seat related to wear or something like, because it friction and impact to valve and valve seats. Then the second question regarding our common issue of ethanol content in fuel. How about the durability of the new developed laser clad valve seat to the ethanol content in the fuel compared to our current technology using nickel-based valve seats or more noble valve seats like that? And then overall, is there any issue in new developer engine to the ethanol? Okay, that's my question. Thank you.
Okay, thank you for the questions. Sorry, namanya siapa tadi?
Mukhlis.
Oh, Pak Mukhlis.
Dari BRIN.
Okay, thank you, Pak Mukhlis from BRIN. Yeah. The first question is about the durability itself. Yeah. Okay. Maybe I need to declare maybe Toyota Motor Manufacturing actually is a manufacturing company. This is manufacturing company, and of course for the research and development is done in Toyota Asia. Maybe Toyota Asia is also we have research and development, and also in Toyota Japan. So we focusing in manufacturing. But of course, this design is, I think our designers already guaranteed that this is better than. Better means not said that the like nickel based press fitting is worse. Of course, the product there is positive and negative, but by making the laser cladding process, this is possible to make like a tumbles combustions and something. That's the benefit. Yeah. And of course, we can guarantee the like durability of the engine itself. Even the nickel combustion, I think our engines also, so far, for me itself, I never heard about we need to replace the valve seat. That's such condition is, I think, not happen. That's about the durability itself. And about the engines regarding the ethanol, I think this is, as I said, we are in engine manufacturers. Maybe I cannot say about the ethanol or something, but this is I think our designers already calculate the impacts of this ethanol portion, because even we also made ethanol engines in our TR. We also making the E100 for the Brazil customer. So we guarantee that the valve can absorb the ethanol portions in the gasolines. That's maybe the. Sorry if I cannot answer further yet. And about the new development, as I said, this laser cut is new technology for us. We just want to make this laser cut process maybe starting 2027. So we know we are developing the machines. So current engine is still made in India. We import from India, and just now we make capacity up because India is very high growth. So now we are preparing our local for the Zenix, because this engine utilized in our Innova Zenix. Yes, thank you. Hopefully this can answer the Pak Mukhlis.
Okay.
Thank you very much.
Thank you very much, Pak Taryono Purba. Due to our limited time, I think we have to move on to the next presenters. But before that, I would like to hand it over again to Mbak Prayang. Thank you, Pak Taryono.
Okay,
Thank you very much.
Thank you
Let's give
very
a big
much.
round of applause again to Pak Taryono Purba.
Yeah, to Pak Taryono, would you please
Pak Taryono, could you
stay?
please stay on
Would you
stage?
please stay here because we have the token of appreciation for our keynote speaker. Would you please to move aside and stand here, Pak Taryono. And now we would like to invite the Dean of FTI, Professor Rianti, to deliver the token of appreciation and accompanied by Dr. Endang Juwana as the Vice Chairman of ISTA-AM. And here as the highest appreciation from the board of ISTA-AM 2025. Thank you very much to our keynote speaker, Bapak Taryono Purba from Toyota Motor Manufacturing Indonesia. And once again, this is the certificate of appreciation for our keynote speaker. And photo session, please, at the stage. Pak Zaki, please welcome to. All right, photo session together. All right, thank you very much, ladies and gentlemen. Please give applause. Thank you very much, Ibu Profesor Rianti, Bapak Dr. Endang, dan juga our keynote speaker, Bapak Taryono Purba. Thank you for the knowledge sharing and the insightful perspective for all of us in here in ISTA-AM 2025. Wishing you can meet again in another good opportunity. Thank you very much. And for the next keynote speech session, I'll pass it back to our moderator, please, Bapak Zaki.
Okay, thank you, Mbak Prayang. Okay, ladies and gentlemen, let's move on to the next presentation. Our next keynote speaker is Associate Professor Nagarajan Raghavan from Singapore University Technology of Design, SUTD. Welcome, Professor Nagarajan. You're joining us through Zoom platform. Very good morning. Thank you for joining us.
Good morning, Dr. Zaki. Good morning.
Thank you. Before we begin with your presentation, just a short bio of Professor Nagarajan. He obtained his PhD in microelectronics in 2012 at the Division of Microelectronics Nanyang Technological University, NTU Singapore, and SM in Advanced Materials for Micro and Nano Systems in 2008, and MAng in Materials Science and Engineering from National University of Singapore and MIT Boston, respectively. He was a postdoctoral fellow at the Inter-University Microelectronics Center, IMEC, in joint association with the Catholic Universiteit Leuven in Belgium from 2012 to 2013. Without further ado, I'll give the presentation time to Professor Nagarajan Raghavan. Thank you, Prof.
Thank you, Dr. Zaki. Let me just share my slide. Can I confirm that you can see my slide?
Yes.
Okay, thank you. Good morning to everyone in Jakarta. Thank you so much for inviting me to this conference as a keynote speaker. My sincere apologies that I could not make it in person due to my personal travel commitments as well. So thank you to Professor Arif Budiman for giving me this opportunity to be in ISTA-AM 2025. I'm very glad to share some of the work that we're doing at SUTD, Singapore University of Technology and Design. And I hope to be able to answer some of the questions you may have at the end of this talk. So, so my name is Professor Nagarajan Raghavan. You can call me as Naga. I am an associate professor at SUTD. It's Singapore's fourth university set up by the Singapore government in 2011. We are a public funded university with bachelor's, master's, and PhD programs. And additive manufacturing is one of the key focus areas of our research pillars as well. So today I'm going to be talking about the work we're doing in my research group that is related to metal additive manufacturing, in specific laser powder bed fusion. And we are kind of looking at how material uncertainty in material properties results in significant performance uncertainties in metal 3D printed devices. So we want to see how uncertainty is an important thing to account for in manufacturing process for metal additive manufacturing, and how it has an impact on the yield strength, which is one of the key mechanical properties of any 3D printed device, and how these are important metrics that we should capture in as part of any manufacturing process, so that we know what are the averages and standard deviations of properties that we want to achieve, and we can hopefully work backwards towards better optimizing the process, not just for improving the mean performance, but also the standard deviation of the performance as well. So just to briefly introduce my group is called Nano Macro Reliability Lab. We have around 10 to 12 people in my research group focusing on design for reliability, design for manufacturing, and design for maintenance of different systems, including electronic devices, automotive electronics, power electronics, additive manufacturing, both metal and polymer-based processes, and battery health management systems as well. And we also play an important role in seeing how machine learning and AI can actually play an important role in design for additive manufacturing in my group. So I think Dr. Zaki has already introduced my background to everyone. So my research is basically on condition health monitoring, prognostics, and physics of failure, design for additive manufacturing, as well as materials design for micro and nano electronic devices. So why study uncertainty quantification in metal additive manufacturing? So I just want to highlight that the focus of my talk today is only on metal additive manufacturing. And in particular, we're just going to look at laser powder bed fusion as an example. But the same approach or framework that we use here can also be applied for other metal additive manufacturing processes, and also for polymer AM processes with slight variations in the framework. So we all know that process variations are part and parcel of any manufacturing process. We can't completely get over it. So it's important for us to understand how things that we cannot fully control, be it laser power or scan speed or hat spacing and so on, the variations in the process parameters will definitely have an impact on the variations in the microstructure of a material, and that microstructure variations will also affect its mechanical properties. So we want to build a framework that can map or quantify the variability of process parameters to the variability of the microstructure, and in turn quantify the impact of variability of the microstructure on the variability of the mechanical properties. So that is basically process structure, property, performance, full workflow. That is what we are trying to build. We're trying to build a framework that can completely help us understand the relationships of all the different things, process structure, property, and performance of additive manufacturing process through a uncertainty quantification modeling framework. So we need to do this because only if we are able to predict what the likely impact of a variation in the process is on the performance, only then will we be able to do an inverse design or some kind of optimization of the process to better control the mechanical properties that we hope to achieve. So that is the end goal of this entire exercise. And as part of this modeling process, we will of course use digital twins and machine learning tools, because they will enable us to reduce the cost of experimentation, because we can't be running a design of experiment with thousands of different process variations. It's going to be a cost prohibitive and time prohibitive as well. So we are leveraging on digital twins and predictive models using machine learning and AI to help us do this optimization and uncertainty quantification in a more efficient way as well. So, let me just go ahead to introduce the specific process that we are looking at. So we have a digital twin, okay, that is specifically built by our collaborators at Institute of High Performance Computing in A*STAR. A*STAR is Singapore's national research agency called Agency for Science, Technology and Research. And our research group works with Institute of High Performance Computing in A*STAR in Singapore. And they have an additive manufacturing digital twin that has already been built. for laser powder bed fusion process. And we are trying to take the digital twin and then further build machine learning platforms into it and see how a combination of the digital twin and machine learning together can help us better quantify the uncertainties in the process and how that can also help us optimize the process in the near future. So this is a framework that we have. So we have many process parameters in the AM process. It could be the laser scan speed, it could be the laser power, it could be the hatch spacing, and many other parameters. We have the geometry of the part that you want to print, which plays a very important role, because whether the geometry is a vertical cylinder or a horizontal cylinder or a cube or a pyramid or whatever shape it is, the geometry has a very important role to play in the entire thermal history that the 3D printed device is going to experience. So geometry plays a very critical role in the whole simulation process to look at the thermal effects of it. And of course, material properties, which include conductivity, thermal conductivity, specific heat capacity, and many other properties. So we look at the combination of all these different design variables and see what impact they have on the thermal simulation of a part scale, the part scale when you have the part. And then from this part scale simulation, we kind of take one single metric that kind of describes the thermal history that has been experienced by the whole part, and that metric is called boundary temperature. And we then use this boundary temperature as an important boundary condition in the powder scale simulations when we do a multi-scale simulation of the powder bed fusion process, including the melt pool, the grain growth, the solidification of the melt pool, and so on. So all of these multi-scale, multi-physics problems are built in the digital twin here, where the boundary temperature is an input to the powder simulations, and the powder scale simulation results are then you get a microstructure of the 3D printed product, and from the microstructure we can then use homogenization methods to estimate the yield strength of the 3D printed device. That's basically our end goal. So these are the design variables we have that we can play with, and this is the performance that we care about. And when I say performance, we don't just care about the mean or average value of the yield strength, but we also care about the variation of the yield strength as well. And in this process, we will of course be using machine learning to map all these dependencies, because running this digital twin for every single combination of values will take a few hours to run just one single simulation. And for us to do thousands of simulations will be computationally very expensive. So we want to use machine learning tools to increase the speed of this simulation by as much as 1,000 to 10,000 times more efficiency, and with a small compromise in the accuracy of 2 to 3%. So we will of course have some compromise to make in machine learning or reduced order models for additive manufacturing, but we have ensured that the accuracy drop is only 2 to 3%. So that is far less compared to the improvement you get in efficiency by 10 power 3 to 10 power 4 times. So this is the entire framework that we have been working with our collaborators in IHPC. So we have a specific heat capacity, density of the material, and thermal conductivity, which are the three material properties that we are varying. And then we will look at the impact of this on the thermal simulations at the part scale. And then we will export the boundary temperature distribution from this simulation here. And this boundary temperature will then be an input to simulate how the powder bed fusion process works, how the melt pool is generated, how the solidification happens, how the grain growth happens, and so on. And for different temperatures, we will have these kind of microstructures. And these microstructures will then be used to estimate the yield strength of the material and the distribution of the yield strength of the material as well. So we have built a surrogate model or a machine learning model for this entire process. And that has helped us increase the computational speed by up to 10 power 4 times, while the accuracy drop is only 2 to 3%. And this model has been quite helpful for us to do the optimization of the whole process as well. Well, I don't have the details, time to go through the details of this process, but I will definitely be able to share the article with you if you're interested to know more about how this machine learning model was built using methods and Gaussian process regression. And these are the details of the powder bed simulation that we have carried out together with our collaborators at IHPC. These are the typical laser powered scanning speed and hatch spacing. And of course, these are just typical values. We have varied our process parameters in a range of plus minus 10 to 20% of these values to see how they impact the overall mechanical property results, both in terms of mean and the variance as well. So here's an example. Here's one of the results of the simulation that talks about how the boundary temperature of the 3D printed part has an impact on the thermal history, which is the temperature versus time graph that you see, and also the cooling rates. So you can see that when the boundary temperature is very high, the cooling rates tend to be very low, which means that it takes a long time to cool. So therefore, the grain sizes are much bigger. The average grain size is bigger. While if the boundary temperature is much lower, it means that the cooling rate is higher, which means that it is likely that your grains are going to be much smaller in size in your entire microstructure. And these grain sizes will then have an impact on the mechanical property of the 3D printed device as well. So here are 4 grain structure maps you can see for 4 different temperatures, ranging from 300 Kelvin to 1200 Kelvin. And you can clearly see that the grains are much bigger in size for the higher temperatures, while they are much smaller and equal in size for the smaller temperature simulation results. And then we map all these grain structures into the statistical distributions. We look at the grain area distribution and the grain volume. And all of this then gets implemented in a homogenization model that helps us estimate the stress strain curves for different process parameter combinations. And from these stress strain curves, we finally estimate the yield strength. And this yield strength is what is the final performance metric that we are concerned about, we care about. The yield strength as a function of boundary temperature is what we show here. You can clearly see that as the boundary temperature increases, the yield strength logically decreases in value. And the trend is of course not a linear trend, but there is a non-linear trend here, and we have used a simple machine learning model called Gaussian process regression to map this dependency, which will then be used later for our optimization routines as well. So to illustrate the impact that this can have on a real use case scenario, we have considered a very simple use case here, where we are trying to 3D print cylindrical bar. In one case, we are printing the cylindrical bar on a base plate in a horizontal direction, so it's horizontally placed on the base plate. While the second one is the same cylindrical bar with the same dimensions, but printed in a vertical direction. So the difference here is that for the horizontal direction, there is a huge base plate. There's a large contact area between the metal printed device and the base plate. So there's sufficient area for thermal heat to be dissipated from the 3D printed stack. When the vertical growth situation, the surface area or interfacial area of contact with the base plate is much smaller, and therefore it's very difficult for heat to be dissipated from the during the melt pool solidification process. Therefore, we will see a big change in the mechanical properties for these 2 scenarios, depending on whether the growth is horizontal or vertical for the same cylinder. So going through the whole simulation routine, you can see that the boundary temperature is plotted in this figure here. You can see that the boundary temperature is quite close to 300 Kelvin for the horizontal bar. Even though when the heat is generated using the laser powder bed fusion process, there is enough surface area in the base plate for heat away from the sample. That's why the temperature is quite uniform and quite low here. But in the context of a vertical cylinder that's being printed, you can see that the temperature gradually increases towards the higher levels of the bar, because it's difficult for heat to be dissipated through the narrow surface contact area with the base plate.
Sorry, Naga, to interrupt. You have 5 more minutes for the talk.
Sure.
Thanks.
Sure. And then, so these results that we have of the thermal map of the horizontal and vertical bars are then extrapolated to look at the yield strength distribution of the horizontal and vertical bar. While they look the same in color, you can see there's a small variation in the blue color here. So the yield strength of a element in the higher end of the cylindrical bar is not the same as the one in the lower end. It is actually different. So the higher end of the bars have a lower yield strength compared to the lower end of the bar, of the vertical bar. But the horizontal case, it looks like uniform, as we expect to see because of the thermal dissipation of the heat. And then we bring in the other quantification here by looking at how the material properties have an impact on this boundary temperature, and how the variation in boundary temperature will have an impact on the variation in the yield strength. So the properties that we vary are the thermal conductivity, specific heat, and the material density. And then we do our Monte Carlo simulations here, and then see how the yield strength distribution changes with boundary temperature, both along the x-axis for the horizontal bar and along the z-axis for the vertical bar. And then we use the Gaussian process to model this statistical relationship, and then we embed machine learning model into this entire workflow of how uncertainties in the input knobs, input time variables may have an impact on the yield strength distribution at the output level. And these are the histograms of the yield strength you can see here, based on the uncertainties in the material properties, based on the digital twin that we have developed along with the machine learning model as well. So with this kind of analysis, this is basically what we wanted end of the day. And with this kind of analysis, we can see that you know what is the mean. You also know what the variation of the mechanical properties is. And with these two histograms, you can then work backwards using the machine learning framework to see what the real design variable properties should be, what should be the optimal material properties or process parameter conditions to minimize the variation and maximize the yield strength that you want to achieve. That is what we want to achieve as part of the inverse design framework. So to conclude my talk, I want to mention again that uncertainty quantification is an important part of qualifying a manufacturing process for metal additive manufacturing, and it plays a very significant role in inverse design, in optimization, and also in digital certification of AM design plans in the future, because we can't be manufacturing every new 3D printed CAD design for validation. So we want to be able to digitally certify an AM process and an AM design through this machine learning and digital twin framework in the future, hoping that will significantly reduce cost and time for designs to be validated and manufactured for better use end of the day. So with that, I would like to end my talk. I would like to thank Professor Arif again and Dr. Zaki as well, and members of my team at SUTD, and also the Digital Manufacturing Design Center in SUTD that has funded this research, along with my collaborators at IHPC who have also been a key part of this research work. Thank you to the organizing committee, and I'll be happy to take any questions from your side. Thank you.
Thank you very much, Professor Nagarajan Ragavan, for a wonderful presentation. Now I would like to invite the audience to ask questions to Professor Nagarajan. Maybe I'll take one question from the audience presenting here in the auditorium, and I also want to invite attendees on Zoom platform. If they have any question, they can also ask their questions in the chat box. But first, maybe a question from the audience that is in this auditorium. In the chat box, if, through Zoom meeting, any questions? Or maybe I can start with one. I have a question about your slide number 12 on the computational domain. You were showing that it seems that the domain is not like full scan path of AM. Is that so?
You're right. So we have chosen a single scan region for the simulation because the entire scan simulation would take a very long time for us to do. So we've chosen a single scanning path along the straight line to kind of simulate the process, but we are also able to extend the scan path to have a raster scanning pattern as well if necessary.
Okay. Yeah. And the simulation, the part scale simulation that you showed, that's only like a pure conduction model with some kind of effective thermal conductivity to account for the melt pool flow. Is that so?
Yes. Okay. So part scale simulation is a low fidelity model that purely looks at the thermal, the differential equations that govern the thermal process. But the powder scale simulations are a multi-physics process that includes, melting, resolidification, grain growth, nucleation, and all of that. Yeah.
Okay, thank you. Maybe other questions from the audience? Maybe one more from me because the topic is quite interesting and it's really related to my work. Maybe just one more for me. Naga, what's the typical running time for your simulation for this AMDT? I mean, on the slide that you showed on slide number 12, what's the typical running time?
Yeah, so the typical running time is around, I would say 3 to 4 hours on a high performance server. So it takes 3 to 4 hours for a single run of the simulation to be done. And that's the reason why we have decided to use machine learning as a very important tool in this whole workflow. Yeah.
Okay. In view of time, I think we can end the session for keynote speech this morning. Thank you very much again, Naga, for your talk. I think it's an impressive work and will add much to the quality of our conference today. Thank you again, Professor Nagarajagavan. But before leaving, small token of appreciation from our side. Of course, you're not present with us here, but we have like some digital certificate to show, just to show our small token of appreciation for your work and for your talk.
Thank you.
Slide presentasi, slide certificate-nya bisa ditampilkan. Yeah, okay. Everyone, let's thank Professor Nagarajagavan again for his keynote speech.
Thank you so much. Thank you so much.
This is our certificate for you. Thank you very much, Naga.
Thank you so much. Thank you. Thank you.
So
Thanks
with this,
a
I
lot.
would like, Bapak yang singkat.
Thank you very much, Dr. Zaki as moderator, and also our Dean from Faculty Industrial Technology Universitas Trisakti, Ibu Profesor Yanti, would like to express the appreciation to Professor Nagarayan. Please, Prof.
Thank you, Mbak Prayang.
Thank you.
Professor Naga, hello.
Hello, hi.
Nice to meet you. Thank you very much.
Thank you so much. My pleasure. Thank you so much. Sorry that I was not able to come in person. Thank you so much.
It's okay. I hope one day you can come and visit us here.
Definitely,
And
definitely.
give us
Yes.
some general lecture, because what you give us is very, very interesting.
Sure.
And we do
Thank
hope
you so
that
much.
one day we can meet and we can discuss about this matter again.
Definitely.
Once again, thank you very much. What you give us inspiring us very much. Okay, thank you.
Thank you. Thank you. Thank you.
Thank you, Ibu Prof. Yanti. Once again, give applause, ladies and gentlemen, to our keynote speaker, Professor Nagarajagavan. Thank you very much for the insightful presentation and for the sharing knowledge. All right, so ladies and gentlemen, that's the end of the keynote speech session, and now we are straightly continue for the parallel session. And for all presenter, you may attend the presentation room at 7th floor. And also, if you need further information according to your room, you can ask the registration team. And don't forget, after the parallel session, we still have the awarding session and followed by closing ceremony later on after the presentation parallel session. Thank you very much, and we'll see you again. Assalamualaikum warahmatullahi wabarakatuh.
Time, I will protect you from all around you. I will be here, don't you cry. explain. I know we're different, but deep inside us, we're not that different at all. We're not that different, and you'll be in my heart. Yes, you'll be in my heart from this day on, now and forevermore. Don't listen to them, 'cause what do they know? We need each other to have and to hold. They'll see in time. I know when destiny calls you, you must be strong. I may not be with you, but you got to hold on. They'll see in time. I know. Show them together, 'cause you'll be in my heart. Yes, you'll be in my heart from this day on, now and forevermore. You'll be in my heart, no matter what they say. You'll be here in my heart always.
Dari kejauhan tergambar cerita tentang kita, terpisah jarak dan waktu. Ingin ku ungkapkan rindu lewat kata indah. Tak cukup untuk dirimu, sebab kau terlalu indah. Dari sekedar kata, dunia berhenti sejenak menikmati indahmu. Dan apabila tak bersamamu, ku pastikan ku jalani dunia tak seindah kemarin. Sederhana, tertawamu sudah cukup lengkapi sempurnanya hidup bersamamu. Jika hariku lalui tanpa hawamu, percuma senyumku dengan dia. Oh, dan apabila tak bersamamu, ku pastikan ku jalani dunia tak seindah kemarin. Sederhana, tertawamu sudah cukup lengkapi sempurnanya hidup bersamamu. bisikanmu di antara bayang-bayangmu terucap kata cinta.